Hello, and welcome to your Mendel and Morgan test review. I'm going to start off this story with pedigrees. Pedigrees are these diagrams that are on the right of your screen. They are a series of circles and squares that represent men and women and any disorder and or characteristic trait they may have. So if you look at basically what the rule of thumb on a pedigree is they are going to allow geneticists to follow disorders or traits. It does not have to be a disorder. It could be a trait through a family. It could be anything. Eye color, hair color, whatever. It doesn't matter. If you are unsure of your potential for any kind of genetic disorder, the scientist will always, of course, ask you if you or your parents or your grandparents have had any of these disorders. And that's pretty much where they start. So let's start off with this first pedigree. In this first pedigree, two things have to jump out at you. One, that in this case only squares are colored in, so that means it's going to affect males only in this pedigree, and that you could have an affected male from parents that are themselves unaffected. So those are two giant clues that have to jump out at you and say this is definitely a recessive disorder, and this is probably an X-linked recessive. The X-linked is what will give you the clue that it's mostly males, and recessive, well, let's do the obvious clues. Mostly males, in this case they're all males, but in a normal pedigree they would be mostly males, and the parents are unaffected, but their child is. I'll explain that in 1 second. So you can see here, and I already have an arrow, that the family there, the mother and the father that started this pedigree, are white. So in this case, that means they do not have whatever the disorder is. This girl here, which is their daughter, also does not have the disorder, but their son does. And as you can see, the son did not pass down the trait to his daughter, as you can see following this way, the daughter does not, but she then passed it on to her son. So another good clue on recessive disorders is in this particular line, there was a generation that was skipped. If you look here, this generation was skipped in that family, but it showed up again in their kids. So a couple of giant clues on recessive is that the parents are unaffected and the child is. So in this case, we said it's X-linked recessive. So let's see, an affected male. Now the way we write that will be X minus Y. XY says it's a male. That minus sign there lets you know that that is the affected problem. With a carrier female. So the carrier female means that she is X minus X. Now a female can be a carrier for a recessive X-linked disorder because she has two X's to play with. In the boys, they only have one. So this is a unique case because you will actually get a female with an X-linked recessive disorder. Rare, but it can happen. Here you will have a male with the disorder. Here you will have a female carrier. And here you will have a male that does not have the disorder at all. And again, men cannot be carriers for X-linked recessive disorders. So those are your big giant clues. Now this case here is rare, but it can happen. Let's look at the next pedigree. Now the next pedigree is, again, it's kind of like a little bit of a cheat here. These are kind of like super light on the shade. So that was a giveaway. I was hoping that didn't happen. But anyway, what you need to see here is that since they are not colored in totally, they are unaffected with whatever the disorder is. They're carriers, in this case, but they're unaffected. Now, if you look, their children, this male and this female, both have the disorder, but that female does not. This male here is a carrier, and this female is a carrier. So they actually had a lot of kids. 1, 2, 3, 4. They had 5 kids. So in an autosomal recessive disorder, what that means is that it does not matter if you are a male or a female. It is on the autosomal chromosomes 1 through 22, and that, again, the parents can be carriers and be unaffected. So once again, clues, both boys and girls could be affected. It does not target only one sex. And again, the parents are unaffected with whatever it is. Again, color blindness. I'm not scratch that, not here. This would be something like cystic fibrosis or Tay-Sachs. So if we wanted to do just a kind of couple of practice genotypes, let's use, I don't know, let's use E's. Let's say that the double E is affected. So you know for a fact that these two have to be double E. Well, if the kids are double E and the parents are unaffected, the parent's genotype would have to be capital E, lowercase e, capital E, lowercase e, which means they are both carriers. Now, it's shaded, so it's kind of a cheat, but this boy you know is capital lower. He is a carrier. This girl is capital lower. She's also a carrier. And they left this girl here totally kind of unaffected, so she got the capital and the capital. This woman here, if she had any kids, would have nothing to worry about. In this case over here, this carrier, this male carrier, happened to marry a female that was double capital, so technically their kids have nothing to worry about. There may be a carrier in there, but they will not have the disorder. So those are your biggies on X-linked recessive and autosomal recessive disorders. Now let's kind of jump ship here for a second and let's go over to our boy Mendel. Now when I talk about Mendel, I am pretty much talking about complete dominance. And what complete dominance means is if the dominant trait is present, it shows up. So in this case, we started off with a pure dominant, for any trait, it doesn't matter what it is, and a pure recessive. That's otherwise known as the P generation or true breeding. So let's go with T's. This parent is tall, this parent is short. Since it is complete dominance, all of the offspring will be tall. No intermediates, no mediums, no smalls. They are all tall. And that is pure dominance, where if one dominant allele is there, it shows up in the trait. Now what Mendel then did, that once again is known as the F1 generation. That's what you just made. The F1 generation is all of those capital T, lowercase t's, or all heterozygous. He then took the F1, two of the F1s, and he crossed them. Once again, that one's capital lower, so both of these parents are tall. He then, made some seeds or grew the plants, and he found out that most of them were tall, which is what he expected. But all of a sudden, what happened in that little bottom corner there? But the recessive trait showed up. So the recessive trait shows up 25% of the time. So in the F2 generation, which is what that box represents, that is a 3-to-1 phenotypic ratio or a 1:2-to-1 genotypic ratio. Either way, the recessive kind of showed up. So in this case, you could actually have a recessive with two dominant looking parents. And that led him to understand one of his laws known as the law of segregation. And what that says is you can only give one of your two alleles at any one time. That's what led to that spot down there in the bottom right corner, or the pure recessive. So now he had a problem because he didn't know if he had a tall plant, if that tall plant was a pure tall or it was a heterozygous tall. So he came up with something fancy called a test cross. And here's what he did. He took a plant that he thought might be tall and a plant that he thought might be tall, and they're both tall. They are technically at this point unknown to him. Let's just pretend he didn't know. And what he did was he crossed them with a pure recessive. Now if you do that, you're going to get an interesting result. Here, this is exactly what you did before in the P generation, where every single one of the offspring is tall. That let you know that you had a homozygous dominant tall. But if you end up with a 50-50 split, meaning you have tall, tall, short, short, this is now basically a 50-50 split, or half and half. That is a true test cross, and that shows that what you thought was dominant here, what you thought might have been pure dominant, was not. So that's how we do a test cross, and that's how you can figure out in any sample if what you think may be pure homozygous dominant, well, it might not be. Now for our other fun bit of Mendelness, but this is kind of after Mendel. And this is something called incomplete dominance. And incomplete dominance is where you get something in the middle, something blended, something maybe in the intermediate family. And again, you can do this any way you want. We talked about this in class. But blue, in this case, I'm going to make capital B, capital B. That's just what I'm going to do. And I'm going to make yellow lowercase b, lowercase b. That's what I'm choosing. So there's my blue, and there's my yellow. Well, when they crossed, you normally would get all blue, correct? Except if you have what is known as incomplete dominance. And this is where the blue does not win, the yellow does not lose. There is a nice blend where you get green, in this case. It could happen with red and white making pink, black and white making gray, whatever. So in this case, we're green. Now what if you then take a couple of your green offspring and you cross them? Well, you'd be shocked to find out. You may get blue, you may get what you would expect, a couple of greens, and there's your yellow. Once again, this time the genotypic and phenotypic ratio is a 1:2 to 1. That does not happen with Mendel's regular complete dominance. Well, and we have codominance. Well, codominance is where everybody wants to win. So in roan cows, which we talked about, you take a red cow, you take a white cow, and the babies are red and white. So they're not pink, they're red and white, where they both win. Human blood, multiple alleles human blood, is also codominant. And the way you're going to write this is, if mom is blood type AB, which it says, capital IA, capital IB, because remember, blood is codominant. A is dominant and B is dominant. Well, dad is blood type O, which is the pure recessive. So there's your two lowercase i's. And what you're going to end up with is a kid that either has blood type A, or blood type B, or blood type A, or blood type B. These two particular parents cannot have a kid that is type O, and they cannot have a kid that is type AB. Just how it works. Well, what if mom is A and dad is B, and, well, I don't tell you if they're pure A or they're heterozygous A, but of course I'm being nasty and asking you if they can have a child with type O. Well, they can, if mom is capital IA, little I, dad is BI, and, well, they could have a kid that is blood type AB. That would be kind of cool. I wish I was blood type AB. They could have a kid that's type B. They could have a kid that's type A. And believe it or not, they can actually have a kid that is blood type O. Because if both of the parents were not pure blood type A or blood type B, they actually carry with them that recessive allele. So A is dominant, B is dominant, and A and B are codominant. Well, let's go back to some X-linked traits here. X-linked traits, again, talked about it earlier, we're kind of mixing up a little bit. They are anything that is found on the X chromosome. Once again, they can be a disorder or a trait. So in the case of humans, hemophilia, color blindness, those might be some disorders. But if you are a fly, then that is your trait. So if you are an X-linked fly, that is your eye color. And we're going to talk a little bit more about that coming up in a little bit. Well, we talked about it in class that if you have an X-linked dominant trait, you only need one copy. It's going to act very much like a autosomal dominant trait, but it does matter who brings the trait to the table. So in this particular example, let's see. Dad has the X-linked dominant disorder, whatever it is, and Mom does not. And you know that because I am designating the capital D as the dominant X-linked disorder. That's what I'm telling you. Well, unfortunately for all of the girls, they are all going to have whatever it is because they got the capital D from their mom. And since it's dominant, it actually beats over the lowercase d, and, well, that's what happens. But in this case, good news for the boys, none of them are going to have an X-linked dominant disorder. So in the world of dominant disorders, boys got away with one if Dad was affected. Well, the story is different if Mom is affected. And watch what happens. Watch how different this is. Let's say Mom has an affected, bad copy, if you will. And there's her good one. If this was X-linked recessive, no big deal, but it's X-linked dominant, so unfortunately there are no carriers. Let's say Dad is all good. In this case, watch the difference here. Well, that's a lowercase d. This female has it, but this female does not. So that's kind of cool. This male has it, this male does not. So if Mom brings the X-linked dominant disorder, half of all kids are affected, boys and girls. In the world of if Dad brings it, then only the girls are affected. So those are the kind of things you just have to work it through, make the Punnett square. Now this one here gave kids in class a lot of trouble, but let's read it very, very carefully. I spent a lot of time telling you that the eye color in flies was determined by the X chromosome. I spent a lot of time telling you that. X-linked recessive, we talked about that. Well, after further, I guess we'll call it investigation, they found that fruit flies could have red eyes. Well, we know that. That's R. They could have what's called sepia eyes, which is kind of like a goldish color. Or they could have white eyes. Well, how are we going to do that if capital R is red and lowercase r is sepia? I don't see white. Well, the color, if it's expressed, is on the X chromosome. So let's read it carefully. The color of eyes, either red or sepia, is autosomal. That means it's not a sex chromosome. So basically males and females could both have red or sepia eyes. It can happen. But remember, I told you there's an X-linked component, and this is where I guess it really makes a big deal. So let's kind of zoom in over here. In these examples, notice that's a female, that's a female, this one's a male. And you know that because the females have two X's and the males have only one. If there is at least one capital T associated with those X's, that means that color will be expressed in the eyes, which means they will either be red or they will be sepia. If, however, there is no capital T, for example, here there are two lowercase t's, or here there's only one lowercase t, because there are no caps, no capital T, it's going to wipe out the color as even happening. So these two genes are kind of associated with each other. So, let me explain. Let's get rid of this because it looks blurry. How could I have a female with red eyes? Well, I have to start with either X capital T, X capital T, or X capital T, X lowercase t. Because as long as I have one capital, will I be able to have a color eyes? And my red eyes are either going to come from capital R, or capital R, lowercase r. So any combination here, 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 or here is going to give you a female with red eyes. Well, in this case, next one example, I have a female with white eyes. Now watch the difference. There's my two X's, but notice I have two lowercase t's. So therefore, that wipes out the color of the eyes. So it does not matter if I'm this, or if I'm this. Because there's no capital T's, these genes do not get expressed. Now, one of the kids asked, well, why do they have them? Why are there R's if they're not going to be expressed? There has to be all of the genes in all of the chromosomes. There has to be. You can't just leave things out. But this determines if that color is expressed or not. So now, let's go with a male with sepia. Now, sepia is the recessive trait, so there's only one way to write this. X, capital T, Y, lowercase r, lowercase r. That is a male with sepia. Now, a male with red, there are two ways to write it. You can either write it X, capital T, Y. This is red eyes, and so is this. So, in order to show the color, you need at least one capital T. If you do not have a capital T, like in our second example, well, then the color, the red or the sepia, does not show. So that's how one, we'll call it gene, can affect another. That is how dogs, like labs, come in different colors. Okay. Well, later on, as fate would have it, after all this stuff, they then discovered that some genes were known as linked. Now, what that meant was, if you had a chromosome like this, and you had two genes that were right next to each other, when crossing over occurs, which means it takes a little piece of one chromosome and swaps it with another one, those two traits are likely to go together, hence the term linked. Now, it's not guaranteed, but it's highly likely. So that means that they will not segregate independently if they are linked. But they could, and that's why things get a little annoying. There is a tiny, tiny, tiny chance if the two genes are not piled on top of each other. If two traits are totally not linked at all, what that would mean, if they're not linked totally, that means they're on different chromosomes. So, for example, in humans, hair color and eye color, they are not linked. So you have an equal chance of getting a kid with brown eyes or blue eyes or blonde hair or brown hair, depending, as long as the possibility is there in the family. In Mendel, his height, his pea color, his pea shape, his pod color, whatever, all of those things were on different chromosomes, so therefore they all kind of assorted independently because they were not linked. So in this first example, let's say that I am linking together awesomeness and, I don't know, whatever, bigness or whatever, doesn't matter. So if I'm telling you that they're linked, let's see what we got here. I see one parent is capital A, capital A, capital B, capital B. That means this person is extremely awesome, right? And this person is very big. And life is good for them. Well, what if I cross them with a lame-o, small person? Well, awesome and big are dominant. So what's going to happen to the kids if you do that cross? Well, hey, they're all going to be awesome and they're all going to be big. But will you have the chance to give smallness or to give lameness? Is it possible? The answer is yes. So I do a test cross and I say, okay, I have my awesome big parent. That's heterozygous. See this? Be careful. This is a dihybrid, so be careful. Or it's two hybrid traits, whatever. And here, this is my pure recessive, so this is a test cross. So let's see what we got. My kids could be awesome and big. They could. They could be awesome and small. Well, that wouldn't be very good, would it? They could be lame and big, or they could be lame and small. So those are our choices. Now, if these genes were linked, that means they were on the same chromosome near each other. Most of the offspring, I'm going to make up a number, 251 offspring, and let's say 246 offspring are going to resemble each parent. These guys are what are known as recombinants. Now, what a recombinant means is they are half of one parent and half of the other. So let's say that I'm going to make this up, 16 of these and 14 of these. Now, if you notice, there is a huge difference between 16 and 246. So that means these recombinants are very unlikely to happen. That means that the genes must be very, very, very close to each other on the same chromosome. So now let's do a math problem and see how it works. In this case, I took parents that were, in this case, awesome and small. So that's one parent. And the other parent was lame and big. Okay, so that's fine. And they have a whole bunch of kids. If you notice, 431 of them are awesome and small, just like, let's say, Mom. 428 of them are lame and big, let's say, like Dad. Does that make sense? If they're linked. It does. Now these guys, 18 are awesome and big, that's one of each, and 19 are lame and small, well, that's one of each too. So these guys are your recombinants. Now the way that you do this is you take the total number of recombinants divided by the total number of individuals or the total number of kids or whatever you want to call it, and then you're going to multiply that by 100. And that's going to give you what is known as a crossover frequency, which can be converted to what are known as map units. So in this case, 18 plus 19 is 37. That's my number of recombinants. That's the 18 and the 19. Now I have to put the total on the bottom. So now I got to add 431 and 428. And my total offspring of all of my kids here is 896. So I'm going to just simply do that math and multiply it by 100. So 37 divided by 896 is going to be about 4.1%. So if I round that to a whole number, I'm going to round that to 4. Now what that means is these things are 4 map units apart from each other. They're close. The closer they are, or the smaller that number, the more likely they are to be linked and travel together. So what the heck is a gene map? What does that even mean? Well, let's take a look. In this case, I have some traits. I got A, I got B, I got C, and I got D. And they're a certain distance away from each other on a chromosome. Now if I look at A and B are very far apart from each other. According to this, they are 37 map units. Now the max is 50. So is 37 pretty far apart? It is. What is the likelihood of those being linked? Almost 0. Now, I look and I go, all right, see, what else do I know? Well, I know B and C are 10 map units apart, so I can go ahead and put a little C right there. And does everybody agree that that represents 10? This total space here between A and B represents 37. Now it's just a matter of fitting everybody in. So I got that out of the way. Now I know A and D are 15 apart, so I go ahead and I put my D right there, and I tell you that they're 15 apart. Well, 15 plus 10 equals 25. If I take that away from 37, that gives me a total of 12. And when I go back to my number, look how far C and D are away from each other. 12 map units. So that is how you do a map. We're going to practice another one when we're done here, but let's just kind of get through this. All right. Now this one here, one of my favorite things to do, is the law of multiplication. In here, you can either draw it a Punnett square, which is ridiculous because it'll take you forever, or you can do what is known as the law of multiplication. So we're going to do the first 2 as a Punnett square so you can see what I'm talking about. So let's kind of do the first 2. And the first 2 And again, you could draw all the Punnett squares you want, but remember, you don't have all day here. So capital A, that's that parent right there, Lowercase a, that's that parent right there. And if we're to do a Punnett square for like the 80 millionth time, this is what we will get. All of the offspring will look like that. So what are the odds of having capital A lowercase a? Well, it is 100%, or 1, because 1 is the highest you can get. Well, what is the odds of getting capital A from those two parents? That answer is 0%, because do you see any capital A's in here with the other capital A? I don't see that, so that's why it's 0%. Well, now we got a problem, because I don't want to have to start drawing out 8 million Punnett squares. That's annoying. So the more you get comfortable with this, the faster you can do this. So let's look. Capital G, lowercase, capital lowercase. What are the odds from that pairing of getting a capital and a lowercase? And if you do that, the answer is 1/2. If I have capital T, lowercase t, what are my odds of getting 2 lowercase t's? Well, that's going to be 1/4. So my total chance of this happening from those two parents is 1/8 of the time. That will happen. 1 out of 8 chances. Okay, let's go here. Capital Y, lowercase y, capital lower. What are the odds of me getting 2 lowercases? Well, we just did that, so that's 1/4 of a chance. Capital lower, what's the odds of me getting 2 capitals? Well, that's also 1/4 of a chance. So what's my total? 1/16. That means in 16 tries, this is the chance I'll get that genotype from those two parents. Well, the only thing that makes this next one more difficult is there's 3 things to do, but it's no big deal. Whoa, this is a test cross, so you know you're going to have a 50-50 chance of getting that. 1/2. Capital lower, odds of getting 2 lowercases. We just did that. That's 1/4 of the time. And now, capital lower, capital, what are the odds of getting capital? Well, that's also 1/2. So if you do your law of multiplication, you will again get 1/16. And that's all you got to do. Now, once again, if you want to do the Punnett squares, you can. You don't have to. And finally, there will be one chi-square question on your test. And here's what we got. In any chi-square, there's a couple of things we need to know. First off, that square right there, you don't have to square anything. So don't square anything with that. It's just called chi-square. Don't be fooled on that. Now, let's see what we got. That fancy symbol is going to be the summation of a bunch of things. We'll see what those bunch of things are in a second. O is your observed value. That's what you counted or you saw. And E is the expected value. Getting that is a little bit more annoying, but let's see what we got. In this case, I am crossing capital T, capital lower, let's see. So this is a tall plant, let's just say, and this is a tall plant, let's just say. And we know that that one's going to be tall, and well, that one's going to be tall, and well, that one's going to be tall, and oh no, that one's going to be short, but okay. But that's not what I care about. I care about the genotypes. Well, let's see what we got. These are our observed values. I observed 56 capital T, 104 capital lower, 52 lower. That's what I observed. But what is my expected value? Well, that's where things get a little tricky. And the way to do the expected value is first you have to get the total of these guys. And the total of all of these is 212. So if you add those up, you're going to get a total of 212 plants, let's just say. Well, if I look at my box, 25% of them have to be capital T. So the way to get my expected is I take my total of 212, and I'm going to multiply it by 1/4, because what's my chance but 1/4 of the time that's going to happen. If I want to get my capital lowercase, that's going to happen a half of the time. So I have to multiply it by a half. And my lowercase is going to also happen a quarter of the time. So I take my 212 and I multiply it by a quarter. Now, those of you that are savvy with math, you know that multiplying by a quarter is the same as dividing by 4. So, for my capital T, I counted 56, but I should have 53. So my expected value is 53. I got 56. All right, that's fine. 212, my expected is 106. I got 104. That's pretty close. And here my expected is 53, and I got 52. So far, I would say my numbers are pretty close. So here's how you do chi-square. It is the sum of the observed minus the expected squared over the expected. So let's see what we got. Observed 56 minus expected 53. That's going to be 3. But what do I got to do to that? Square it. Divided by the expected value, in this case, was 53. Well, let's do the next one. 104. It is observed minus expected. That's going to be negative 2. But that's okay, because what happens when I square negative 2? It becomes 4. Nice positive number, so I don't really care. Divided by, once again, the expected, in this case, of 106. Here, 52 minus 53 is negative 1, but I don't care because that's going to be squared, divided by, again, this time 53. Now, when you do these questions, you must be very, very, very careful. See what they want you to round it to. So now let's do our math, because remember, it's a summation. So the first one is going to be 9 divided by 53. That's 3 squared divided by 53. Rounded to the hundredths is going to be 0.17. The next one is going to be negative 2 squared, which is really 4. And 4 divided by 106 equals 0.04. And then this one here, negative 1 squared, which is 1, divided by 53, is going to be 0.02. So if you add all these up, you're going to get a total of 0.23. That's your chi-square value. That's your chi-square. Well, what should the chi-square be? Well, that you need a couple of things. First, you need these things called degrees of freedom, which is whatever your total outcomes are. In this case, there are 3 choices. Minus 1, so it's your choice, minus 1. So 3 minus 1 is 2, so that's our degrees of freedom right there. And we always go to the 0.05 column, which is 95% certainty. And my table value is 5.99. So my table value is 5.99. My value is 0.23. If your value is less than the table, you accept what is known as the null hypothesis. In this case, the null hypothesis is 25% should have been capital T capital, 50 capital lower, 25% lower lower. Your numbers were really close. You almost got that exactly. So therefore, you accept the null. If your chi-square was like 12.44, that means you're way off. And then you would reject the null. So hopefully all of that helps, and good luck tomorrow.